One of the most elegant and important applications of the Maxwell-Boltzmann distribution is the so-called Equipartition Theorem. What does it say? Well, suppose I can write the energy of a molecule or any other particle in terms of a whole bunch of quadratic terms, independent quadratic terms, that is. For example, ax squared plus by squared plus whatever. Okay, none of these things depend on x. Now, by the way, this x does not have to be x coordinate. It can be even vx, can be vy, whatever. Okay, it's just an independent variable, ax squared. Then it turns out that we can easily calculate the average value of this quadratic term, and you will find the result to be highly simple and elegant. It has nothing to do with what x is. It has nothing to do even with that value of a. It's very, very simple. Let's do this calculation, shall we? What is the average value of ax squared? Well, we use the Maxwell-Boltzmann distribution, right? So it is equal to ax squared times the corresponding probability of finding a particle to be with to have this much energy. That's e to the negative e over kt, right? Energy over kt, dx times d of whatever. Those are other variables that are independent of x, just like those. Okay, yeah, and of course you have to divide this off. This is the normalization procedure, right? You divide this off by the total probability, which has to be equal to 100%, e to the negative energy over kt, dx times d whatever. Now, if you take a close look, you'll find that it's a good idea to break this energy down into ax squared plus non-x dependent part. That's what we're doing here. Okay, ax squared e to the power negative, here's the x dependent part, ax squared over kt, plus x independent part. Same thing, we do this for the numerator, for the denominator. So take a look. Okay, this part, this part, this part, this part, dy or whatever. These are x independent parts, and there's no difference between these x independent parts in the numerator and the denominator, right? The only difference between the numerator and denominator is just ax squared. So you see, I can cross these non-x dependent part out, and I've simplified this calculation to be only x dependent. And what do we have here? That is just ax squared e to the power ax squared over kt dx divided by e to the power negative ax squared over kt dx. Okay, it is not that hard to evaluate these two integrals. Both these two integrals are standard in mathematical physics, and here is this value for the numerator, and here's this value for the denominator. I have assumed that x can vary from negative to positive infinity. It doesn't really matter if x can only vary from 0 to positive infinity, for example. Then you're going to get an 1/2 here and 1/2 there extra, so they're going to cancel out. Okay, so when you plug these into the value for the numerator denominator, and you find that everything else cancels, pi cancels, a cancels, except there's an extra 1/2 here, and there's an extra power of kt compared with that. So here is the surprisingly elegant and simple result. That is, the average value of this independent quadratic term in the energy expression is equal to 1/2 kt. This is the result of the so-called Equipartition Theorem. So what that tells us, that every independent quadratic term in the expression for particle energy has the same exact average value of 1/2 kt. It has nothing to do with a, and has nothing to do with what x really stands for. So every term gets equal average value. That's why it's called equipartition. Equi means the same. So the energy on average is evenly distributed among every single one of these independent quadratic terms. We actually saw an application of the Equipartition theorem when we calculated pressure. Now remember, from the calculation pressure, we found the average kinetic energy, or to be precise, the translational kinetic energy of a molecule at temperature T to be 3/2 kt. Remember that? We can have a better understanding why it's 3/2 kt. Because after all, this is equal to 1/2 mv squared, right? Now remember, this v is not just one independent term. It's actually this v squared equals vx squared plus vy squared plus vz squared, right? So this is 1/2 m vx squared plus 1/2 m vy squared plus 1/2 m vz squared. Each of them is an independent quadratic term, and we know the average value according to equipartition theorem is 1/2 kt, and then 1/2 kt, 1/2 kt. So add all three of them up, what do you have? 3/2 kt. So you see what we got before is just a special case of this general theorem called equipartition theorem. Why is equipartition theorem so important? Because it allows one to figure out the average value of the molecular energy, okay, which turns out to be dependent on temperature. And then that allows us to figure out the total internal energy of the system as a function of temperature, and from that we can calculate the specific heat values. So next we're going to calculate the molar specific heat, or specific heat per mole, for ideal gases. Alright, now let us use the concept of equipartition theorem to calculate the internal energy of various types of ideal gases. And we're going to use the concept of what's called degree of freedom. Degrees of freedom. Now, suppose I have a monatomic ideal gas. You see, the number of atoms in a molecule actually makes a difference here. Okay, if it's a monatomic ideal gas, each molecule is just an atom. Okay, it's just an atom, very small, and it can move in a three-dimensional space. This is all the energy it has. Remember, there is no intermolecular potential energy because this is an ideal gas. And since just a point particle, pretty much a point particle, you don't have to worry about its spin, you don't have to worry about its rotation or whatever, right? This is all the kinetic energy there is. The only form of energy besides, energy inside the atom, okay? We're not going to talk about that. The overall energy of the atom as it moves around, it's just the kinetic energy of translational motion, 1/2 mvx squared plus 1/2 v squared plus 1/2 vz squared. And from equipartition theorem, the average value of such a particle, since it's made of three independent quadratic terms, each of them has an average value of 1/2 kt. So what do you have here? 3/2 of kt. That's it. Okay, it is directly proportional to temperature. Now, this is the energy on average of every monatomic atom, monatomic molecule. Now, what if I have a whole mole of them, 1 mole? Okay, so I have Avogadro's number. What is the internal energy per mole? Internal energy per mole would be Na times E bar, right? Na times E bar. Okay, so per mole, this is what I have, and you take Na times 3/2 kt. Na times k, that's the ideal, that is the universal gas constant, that's 3/2 RT. So this is the internal energy associated with thermal motion per mole of monatomic ideal gas. And from that, we can calculate the specific heat. We'll do that in just a bit. Okay, you notice that it's 3/2. Why? Because this thing can move three-dimensionally. We say it's got 3 degrees of freedom. What's a degree of freedom? Well, each degree of freedom corresponds to an independent coordinate, which helps you specify the exact location of this particle. In a three-dimensional situation, it takes 3 coordinates, x, y, and z, to uniquely specify the location of this particle. So we say it's got 3 degrees of freedom. Okay, and since the particle is just a point, it cannot, move around. It cannot, it cannot spin around. It cannot rotate, whatever. So 3 degrees of freedom. It's all it takes to specify the configuration of this particle, because we don't have to, figure out how it spins or how it rotates once we know where the particle is. So that's monatomic. We're going to use that result later to calculate the specific heat. Okay, now what about diatomic? If it's a diatomic molecule, then we have, if I draw a model of a diatomic molecule, this is like a dumbbell type of thing, right? To identify this particle, the first thing I have to do is to figure out what the center of mass is. See the center of mass, right? And the center of mass moves around, okay? Therefore, it's got kinetic energy due to the motion of the center of mass, and of course, we can describe that in these 3 terms, okay? that is, each of these terms corresponds to a component due to the translational motion of the center of mass. So we say E equals K translational. This is all translational, but for diatomic, it's more complicated than that. This only tells you where the center of mass is. It takes 3 degrees of freedom, x, y, and z to locate the center of mass. But that is not all, because once you fix the center of mass, you still don't know exactly what is the orientation. Okay, the orientation of this this axis, right? It orients this way, and the question is, how many angles does it take to fix this direction? You know, you might think it takes 3 angles, right? Suppose I have a 3-dimensional coordinate. Let's say, how do I identify the orientation of a vector? Doesn't that take 3 angles? Angle 1, angle 2, and angle 3? Well, actually, you think hard about it, it only takes 2 out of these 3 angles, because there is a relationship between them. Okay, you call this alpha, you call this beta, you call this gamma. It turns out the sum of cosine squared alpha, cosine squared beta, and cosine squared gamma equals 1. Okay, and therefore there are only 2 separate angles that can uniquely determine the orientation. Once you know alpha and beta, for example, gamma is fixed. In other words, you have extra 2 degrees of freedom. And what are the energies associated with it? Well, how about rotational kinetic energy, right? I can write rotational kinetic energy, you know, is something like 1/2 I omega squared. 1/2 I omega squared. This is another quadratic term. Okay? Omega is a variable, right? It's another quadratic term. But remember, to use the equipartition theorem, we want to make sure you have independent quadratic terms. Okay, just like here, v squared is not independent itself. It consists of 3 independent terms, right? How many independent terms does it consist here? Well, since it takes 2 angles to specify the orientation, there must be 2 independent terms for rotation. Okay? I mean, you can think of omega x, omega y, omega z. But the thing is, once omega x, omega y is fixed, omega z is also fixed. It's not independent anymore. There are only 2 independent quadratic terms associated with the rotational energy of the system. So this is really k rotation. And therefore, we say 3 terms for translational motion, 2 terms for rotation. There are 5 degrees of freedom overall. Okay, the extra 2 degrees of freedom fix the orientation of this axis. We're not going to worry about spinning about this axis because the size of each atom is very, very small. So the the rotational inertia about this axis is virtually 0. Okay, so we have 5 degrees of freedom. Each, I can write a quadratic term for its corresponding energy, and each average value of the 5 terms equals 1/2 kT, and therefore the average value equals to here 5/2 of kT. All right, so E internal per mole for diatomic would be 5/2 RT. Again, we're going to use that result extensively later when we calculate the specific heat of diatomic gases. So you see, for the same temperature, the same number of moles, okay, a diatomic ideal gas has more internal energy than a monatomic. It's because not only can the molecule move from place to place, but it can also rotate, okay, can spin around, and that takes extra energy. So part of the energy goes to translation, another part goes to rotation. That's why it's got extra energy. In other words, if you want to raise the temperature of a diatomic gas compared with a monatomic gas, if everything else being the same, then it takes more energy to heat up the diatomic gas, because you do not only have to increase the kinetic energy of translational motion, you must also give some energy to rotation. Okay, finally, what about polyatomic? So it's, it goes beyond 2 atoms, okay, it's, 3 or 10 atoms, whatever. In general, we call it polyatomic. So in this case, we have a whole bunch of molecules, a whole bunch of atoms. Here is a whole molecule, which is made of a whole bunch of atoms, okay, more than 2. Now, we can classify its motion into 3 categories, right? One is the translational motion, the whole molecule moving from place to place, and that can be specified by the center of mass, okay? And that takes 3, again, 3 independent quadratic terms, this term, and this term. Okay, so the energy has its quadratic, has its translational part, kT, plus its rotational part, kr. Now, let's be careful about the rotational part. This time, how do you uniquely identify the rotation of this object? First of all, just like that, we need an axis, okay? So, this tells the general orientation of this molecule. How many angles does it take to do that? It takes 2 angles, remember? Just like that, to fix this axis. But on top of that, this time, this whole thing, it can broaden out in this direction, right? So in other words, the rotational inertia about this axis is no longer close to 0. Rather, if I rotate about it, okay, that's called spin of the molecule. It actually takes some more energy. So 2 angles will fix this orientation of the axis, but there is one more angle that tells you how many degrees did the molecule turn about this axis. Okay, so you see, we have an extra angle we must use to help specify the configuration of rotation. 2 for the orientation of the rotational axis, and 1 for how many degrees did it rotate about that axis. So there are 3 degrees of freedom here. Okay, so 3 degrees of freedom for translation motion, meaning 3 terms, 3 independent quadratic terms for translation motion, 3 independent quadratic terms for rotation, plus what else do we have? Well, remember, each atom in this molecule can oscillate in general, right? When they oscillate in such a way, they may not necessarily change the overall orientation of the molecule, may not necessarily change the center of mass position, because what determines the oscillation is typically internal force, which does not change the center of mass position. And these are called vibration. Translational motion, rotation, and vibration. How many degrees of freedom does the vibration have? Well, a whole lot. Okay, remember, there are n molecules. Okay, n molecules. If there are n atoms making up this molecule, each atom, in principle, can move 3-dimensional, right? So to describe n such 3-dimensional atoms, you need 3n in general, 3n degrees of freedom. And 3 of them becomes translational motion for the whole molecule. 3 of them becomes the rotational degrees of freedom. And how many do we have left? 3n minus 6. So how many vibrational degrees of freedom do we have? 3n minus 6. Okay, what about the overall internal energy of the system for a polyatomic molecule? Well, this guy, for each molecule, this guy has 3 terms. Each term is 1/2 kT on average. This guy also 3 terms, each 1/2 kT. I'm going to leave that out for now. Okay, so as far as the translational and rotational motion is concerned, E internal, okay, E internal in this case would be 6 times half of RT, right? Because there's 6 degrees of freedom. 3 for translation, 3 for rotation. That's 3 RT. Plus, I didn't consider rotational energy yet. Vibrational energy yet. So vibration. Okay, so there are vibrational energy on top of the energy associated with translation and rotational motion. How come I leave the vibrational energy out? Well, you will see this in a minute, okay? But you see, if you only consider translation and rotation, there are different values for different types of atoms, whether it's monatomic, diatomic, or polyatomic.